See whether each number is divisible by 2, 3, 4, 5, 6, 9, or 10. Number 1, 32,715. Is it divisible by 2? No, because it's not even. What's the sum of the digits? 5, 12, 13, 18. Good. 18 is divisible by 3. Is 15 the last two digits? Remember, the rule for 4 isn't the sum of those last two digits. It's the last two digits itself. No, it's not divisible by 4. Divisible by 5? 6, no, because it's not a 2 and 3. Is 18 divisible by 9? And does it end in a 0? No, therefore, it's only those three. 5,265. Is it divisible by 2? No. Sum of the digits. 5 plus 2 is 7. 7 plus 6, 13 plus 5. 18 again. We're looking at 3. 65 divisible by 4? No, but it does end in a 5. Not divisible by 6. Yes, it is divisible by 9, but not divisible by 10. So the same as the first one. Good so far? Third one, 7,475. Not divisible by 2. 11, 18 plus 5 is 23. Not divisible by 3. 75 is not divisible by 4. However, it does end in a 5. 23 is not divisible by 9, nor does it end in a 0. Therefore, 5 is your only one. 840. It is even. The sum of the digits is 12. So divisible by 3. 40 divisible by 4. And then 5, or 0, yes. 2 and 3. 6 divisible by 9. No. Divisible by 10. Good. 2, 3, 4, 5, 6, and 10. Any questions on those? What do you need to be careful with? Is rushing. Okay. Maddie? What do you mean? Each of these, Maddie, have different rules. So anytime I have a number that I'm testing for divisibility, I'll run it through each of these rules. The rule for 2, and this should be in your notes somewhere, right? The rule for 2 is, does the number end in a 0, 2, 4, 6, or 8? Does it? No, so I didn't put a 2 now. The rule for 3 is the sum of the digits. When I add all the digits together, 3 plus 2 plus 7 plus 1 plus 5, I get 18. If 18 is divisible by 3, which it is, then I put 3 down. The rule for 4 says, are these last two digits, so 15. 15 divisible by 4. 16 is, but not 15. So that doesn't work. The rule for 5, does it end in a 5 or 0? Ends in a 5. Therefore, it's divisible by 5. The rule for 6 is it divisible by 2 and 3? No, it's just divisible by 3. The rule for 9 works like 3. Is this number, when I added them together, divisible by 9? And yes, it is. And the rule for 10 is, does the number end in 0? It does not. It ends in 5. So those are all those rules you got to test and go through each and every one. Number 5, find the digits between 0 and 9 that make it divisible by 3. So 2, and then there's this box. So 20-something thousand, 402. And we need to try to figure out what's going to make it divisible by 3. So we have to add up what we have so far. 2 and 4 is 6, plus another 2 is 8. 8 isn't divisible by 3, but 9 is. So if I go one more, that gives me 9. Therefore, it's divisible by 3. Now, you need to be careful, because on the test, there may be more than one possibility here. Like if you were to add them all up and say you were to get 4 instead of 8, you could have it equal 6. So you could put a 2 in there for 6, or you could have it equal 9 with a 5. So sometimes you have a couple of different options. This time you didn't. 6, which of these numbers is prime? Any ideas? Brandon? 3,411. No. How do you know by running 3,411 through your rules that it's not prime? Did you run it through your rules, or did you just say, you know what, that looks like a prime number? Tell the truth. So test it for 3. What's the sum of the digits? 3 plus 4 is 7, plus 1, plus 1. 9. Is 9 divisible by 3? Yeah, so it's divisible by 3. It's actually 53. 53 is actually your prime number there. Okay? Anything on that one, number 6? Just run it through your tests. You know, you should know, you should be smart enough to also recognize, they give you a list like that, they're going to try to trick you into picking something that looks prime. Remember we said prime numbers don't have a look, they just are. 7 through 12. Find the prime factorization of each using a factor tree. I don't need to go through all 6. We can go through any ones you want, but we should start with number 7, which is the 630. First rule in determining prime factorization is come up with 2 factors that will multiply to get the top number, the 630. So ends in a 0, there's one I think of right away, Cal. Oh, fancy. 9 times 70 works. Good. But we'll use 9 times 70, but what was I thinking of, Cheyenne? 63 times 10. So let's use that 9 times 70. Okay? So the 9 would break down to 3 and 3. Those are prime. 70 is 7 times 10, prime. And a 2 and a 5, prime and prime. So from here, 2, how many 3s? And a 5. And a 7. Good? Yes. So do the 63 times 10? Okay. So 63 is what, 7 times 9? And then 2 and 5. So we should have a 2, 2 3s, a 5, and a 7. This will always be the same no matter what you choose to begin with. Okay? As long as everything is done the right way, it doesn't matter what you pick with first. Okay? Any of the other ones there that look maybe more challenging than the others? If you really need it for 64, you can do 64 in your head. What is 64? I'm thinking 8 times 8. Well, what's 8? Your 3-headed monster. So a 3-headed monster combined with another 3-headed monster, 2 to the 6th power. Done. The 525 or the 308? All right, let's look at the 525, which is number 11. Okay, now you could go with the 5, but as you get to this point, you might want to focus on the 25. And if you don't know, think of how many quarters would be in $5.25. 4 quarters to $1, 4 times 5 is 20, plus that extra 1 would be 21. If you don't know that, that's okay. But if you do know that it is divisible by 25, all you'd have to do is this and say, you know, That's fine too. Or if you divide by 5, you could get something else. You can use this process. Okay, it sure beats just staring at it. So 25, 5 squared. 21, 3 and 7. So 3 times 5 squared times 7. So when you do your prime factorization, make sure that you put them in order. Because if you don't put them in order, they're not going to be correct, or at least I'll take some credit off. It depends on what my mood is, I suppose. Your exponents, make sure that you simplify and tidy things up as best you can. Josiah. Seven times what and got 105? No. Yeah? All right. Okay, and then what? And then what?
When I did that,
You broke down the 15 to 3 and 5? So did you get this? Okay. But you can still be done if it's done the right way. Yes?
so if you don't like have like the right order or something like that, so why does it matter if you still get the same answer?
It matters. Because we use this process for other things like GCF, LCM. So it's good to get in the habit of doing it the right way. Right. Or you'll lose points. Well, it depends on, well, now I'm more apt to just call it wrong. Because now you know that that's what I want. And if it doesn't come that way, it's either because you want to be defiant, or then you totally forgot because even after you brought it up. Either way, unacceptable. All right. So GCF, 13 through 15. I don't know how far you got, but any of those that you want to look at first, 13, 14, or 15? 13. 65 and 195. Divisible by 5. What times 5 gives us 65? 13. 13 is prime. So those are 5. So when I put them in order, 5 times 13. 195, again, divisible by 5. Well, if 20 times 5 is 100, 40 times 5 is 200, but I need to go one less, so let's go 39, right? Now again, that being said, you can always still find it this way, okay? 5 is prime. 39, is that prime? You should know from yesterday. 3 times 13. So now with the 195, has a 3, a 5, and a 13. GCF, I want to see what they have in common. So any 3s? No. How about 5? There's a 5. How about a 13? 5 times 13 equals 65. 65 is your GCF.
So you don't have to have
Not for GCF. Which is why you want to make sure that you're getting this down so that when you look at your stuff on Monday, you say, oh yeah, this is GCF. Is this the one where I look for what they have in common, or is this the one I look for what they have that's different? Oh, let me consult my notes, and it'll tell me right here. Brandon. Okay. Sometimes you'll stumble across some shortcuts just by what you pick. It's okay. You have to have a process, though, to make sure that just in case you don't find that, if you don't luck out, how are you going to find it? Okay, do you know what I mean? Okay, what about 14? 42 and 63. Any guesses? What do you think it's going to be? We know they have 7, right? So we'll just kind of keep that in the back of our mind. 6 and 7. So for 42, 63 is 7 times 9. So 3, a 3, and a 7. There's our 7, but it also has a 3. 3 times 7, 21. 21 times 2, 21 times 3. Yeah.
What is the time when, since that last time, we was, when it had like a whole bunch of numbers, like if you had more threes in it and you just, so like you add
That's
another
LCM.
three in it?
We'll get to that. So make sure you have, do you have documentation, Kishana, that this is how you do GCF?
Yeah, I'm good at that. I'm just,
Okay.
I'm-
24 and 60? They have 4. Anything bigger than 4? Yeah. 12.
oh yeah.
It's going to be 12. (16 through 19), name the fraction modeled. Yes, most oftentimes when they're asking that, just like Trinity asked yesterday, they want to know the ratio of the shaded parts. So 3 over 5, right? And 17 should be 2/3. 18 should be 1/4. And 19 out of the 6 little rectangles, 5 are shaded 5/6. Any question there? I would highly recommend, just in case it comes up, if your fraction isn't in simplest form when you do it, make sure that it is by the time you put your final answer down. Okay? There weren't any there that needed it, but definitely something you want to take into consideration. 20 through 23, comparing. 11 12, 7 8. How can I accurately compare two fractions? Only if they have what, Willie? So I need to find out what I can use for a 12 and an 8. And between the two, which one should I look at first? Should I look at my larger number, the 12, or my smaller number, the 8? Trinity. The 12, the larger one. Always look at the larger one first. Ask yourself, first of all, does that 12 work for 8? No. Go to the next multiple of 12. What is it? Does 24 work for 8?
Yes.
So we'll use 24. 12 times the 2 gave me the 24. 11 times the 2 is the 22. 8 times the 3 is 24. 7 times the 3, 21. Therefore, when you compare a 22/24 to a 21, slightly larger than the other. 21, number 21, asks for a 4/7 and a 9/14. So the benefit for you to look at the larger denominator first is you may catch it early. 14, does that 14 work for 7? Then I don't have to do a thing to this one. I just have to convert this one. 7 times 2, 4 times 2 is 8. 8/14 is less than 9/14. 22, same thing. 7/15 to 2/5. Use the larger one, the 15. That works for 5. Convert it to 15th. Times 3 is a 6. Should be greater than. 7/15 is greater than 6/15. And how about 23? 8/16. You can go two ways on this one. can either convert the 2 to the 16th, or I could go opposite and simplify the 8/16. If I simplify the 8/16, what do I get as a fraction in simplest form? It eventually will give me half. However you slice it, it's going to be equal. 24, simplest form. If you think of 24 and you go back to 13, anytime you want to find a fraction in simplest form, you divide the numerator and denominator by their GCF. What was the GCF of 65 and 195 like you just had earlier in the test? Trinity? No, not 13. 65. So when you divide 65 by 65, you get 1 over 3. 21 and 57. Think of your factors for 21. 3, 7, or 21. Of those, which of those would be 57 to be divisible by? 3, 7, or 21? 3. So it should be 7 over, what is 57 divided by 3? 19. 7 over 19. 26 is interesting. They want the fraction in simplest form, but you'll say, that's not a fraction. Not yet. What is it as a fraction? 52 over 100. Now you can simplify it. Divisible by 2. 26 over 50. Divisible by 2. 13/25. (27 and 29). Write each improper fraction as a mixed. Write each mixed as an improper. 27, 42 over 4. 4 goes into 42 10 times with 2 left over equals 10.5. Do you need it to be 10.5? Yes, you do. 7 and 4 21sts. How do I convert to an improper fraction? Multiply 21 times 7. Then add 4. Equals 151 over 21. It's a big one. 29. 6 and 4 7. 6 times 7 is 42. 42 plus 4. 6 over 7. Now, LCM. Question there? LCM between 8 and 10. 8, we already know, is our three-headed monster. 2 times 2 times 2. 10, we know as 2 times 5. Getting to that point is identical to the prime factorization, because that's what it is. It's also identical to the way that you start for GCF, except for the fact that maybe for GCF, you'd write 2 times 2 times 2 instead of 2 to the third. Generally, it's the same thing. Now, with LCM, it's just slightly different, because I'm going to be looking for what they have that's different. However, if they do have something that's the same, like the 2 here and the 2 there, I need to take the one that's bigger based on the exponent. So 2 to the third is definitely bigger than just a regular 2. Remember, circling and crossing off are going to be extremely important to you so you don't reuse factors, okay? And you make sure you use all the ones you're supposed to. This 5, are there any other 5s to choose from? So this is the 5 I have to use. Don't blow it when you get to this point and confuse 2 to the 3rd power with 6. It's not 6. What did we just say 2 to the 3rd power was? 8 times 5, our LCM, is 40. 80 would be a common multiple, just wouldn't be the least common multiple. 26 and 30. 26, we go 2 times 13. 30, we go 5 times 6, which is 2 times 3 times 5. Okay, this will be a doozy. Between a 2 and a 2, are either of them any different from each other? So I need to circle one and cross out the other. I pick one. Here's a 3. Are there any other 3s to choose from? So I'm going to circle it and we'll use it. This 5, anything else? And the 13, nothing else. So what I have is that long multiplication problem, 2 times 3 times 5 times 13. 2 times 3 is 6. 6 times 5 is 30 times 13. 3 times 13, 39, plus the 0, your LCM is 390. So this is, the LCM is one of those lessons where you say, oh, you know what? It's much easier for me to just list the multiples and find the first one that they have in common and say 8, 16, 24, 32, 40, 48, 10, 20, 30, 4. Oh, look at 40 is the first one that they have. Look at how nice that worked out. That was much faster than going through all this other stuff. But here, 26 and 30, it's not so easy. Yeah, you can get to 26 and 52 and 78, but after you get to this point, you have to really start thinking. The 30s might be easy, but you're going to have to do this all the way to 390. Did you save that much time? No. Factor tree is the way to go. Definitely the way to go. It's the way I learned. This is the way I learned way back in the Stone Age, before they had paper and we used a hammer and a chisel on a piece of stone. 16 and 44. Let's look at that last one. So the a factor tree for prime factorization for 6 is 2 times 3. For 16, a 3-headed monster, 8 times another 2 is 2 to the 4th. And 44, 4 times 11, which is 2 squared times 11. Okay, so now that we've got that all square, a 2, 2 to the 4th, and 2 squared, which one? So let's make sure we cross out those other ones so we don't reuse them. A 3, anything else? And an 11. 2 to the 4th, make sure we don't confuse it with 8. We just called it 16 times 3 times 11. Can you do any of these in your head? Okay, so we can go 16 times 33. 18, 4, drop the 0. And 18, 4. 8, 12, 528. It's a big one. Again, sure beats doing the other method. (33 through 35). Write each fraction as a decimal. 4/9. Anytime I want to put any fraction into a decimal that doesn't have a denominator as a power of 10, I'm going to have to turn it into a division problem. 9 always goes on the, because my denominator always goes on the outside. 9 into 4, 9 into 40, 4. Okay, so how am I going to tidy this up and write it the correct way, Brandon? How many 4s am I going to put? 1. That's all we need. 4 is what repeats. That's what I want to put down. Okay. What do you know about the 9 as the denominator? What's 1/9 as a decimal? 0.1 repeating. What's 2/9? 3/9. 0.3 repeating. What was 4/9? 0.4. What's 5/9? 6/9. So there's a little trick with the 9. In fact, you'll see that's how we put repeating decimals back into fractions. But 2/11. Do we need to see that one? Might as well. We got time. Eleven on the outside, 2 on the inside. 11 is not going to 2, but it goes into 20 once. Into 90. Into 20. Into 90. Into 20. Good. What is actually repeating? The 1/8. Okay. I know. Oh. 11/12. So 12 on the outside, 11 on the inside. So again, 12 does not go into 11. 12 into 110. Any suggestions? Well, I'd try 9, right? Why not? 108? Why did I try 9? Why would we try 9? Willie? Yeah, definitely good thinking with the 12 times 10 is 120. But also 11/12 is awfully close to 1 whole. So 0.9 would also be pretty close to 1 whole, right? So would 0.8. But I'll just test the 0.9. 108. Now watch carefully. 2. Drop the 0 once. Into 80. 6 is 72, right? Into 80. Okay, so 0.916 with a bar just over the 6. You really want me to have that? You really want to give that to me? 36. We'll take a peek at 36 yourself, and then we'll come back in a minute and see if you have any strategies or what they're talking about. Just look at it yourself real quick. She told them to draw, color, or paste 42 stars on poster board. The only rule was that the stars had to be in equal groups and the number of stars in each group had to be prime. How many groups of stars might be on a poster and how many stars are in each group? So here's what we need to know. Using 42, what are the possibilities that we could have? We could have one row of, we could have 2 rows, we could have 3 rows of, we could have 6 rows of 7. Knowing that, well, and vice versa, right? I suppose you could also say 42 rows of 1, 21 rows of 2, 14 rows of 3, 7 rows of 6. Essentially the same kind of concept, I suppose. The only rule is the stars had to be in equal groups and the numbers of stars had to be prime. So if we call this the rows and that stars, this number of stars had to be prime. So is this number of stars prime? So that one isn't going to work. Is that number of stars prime? But that one works. Does this work? 42 rows of 1. Is 1 really prime? I mean, I would accept it if you wanted, but if you didn't put it, I would understand too. I don't know where 1 fits in there. How about 21 of 2? 2 is prime, right? It's 3? It's 6. So those could be your possibilities for, you know, putting the stars in the number of rows with the number of stars being prime. (37) How do you use the LCM to write 2 or more fractions with a common denominator? Oh, guys, this is what they're asking. Go back to number 20. How do you use the LCM, least common multiple, to write 2 or more fractions with a common denominator? Here are my 2 fractions. How do I do that? How can you put that in words? So like we said, 12 doesn't work for 8, but the next multiple, 24, did. And then from there, it's basically the same process that you use to convert the fractions to compare them. It's the same. That's all they're asking. Okay, however you want to explain it. You want to use a visual example, that's fine. And since the tests are structured the same, you'll find examples right at that bottom section on the first side, just like we did. So if you want to use that as an example for it, that's fine. Still deciding if I'm going to make these last couple extra credit or just make you do them. We'll see. What we'll probably do for next week is